Hello, everyone, and welcome to our event today. And I am very pleased to welcome you wherever you're joining us from. Today's topic is Hyperloops, feasibility and safety. And we have a very exciting set of presentations and a discussion for you on that topic. So just to kick off the proceedings today, a little bit of housekeeping. My name is Nigel Ward, and I am the host for today's event. I'm going to be taking you through and guiding you through the presentations and the activities today. So we're going to hear some interesting presentations, and then we'll have an opportunity to put some questions and answers. We're going to have a roundtable discussion fed by the questions that you may wish to put forward as you're inspired by what's said today. So Hyperloop's feasibility and safety. Well, Hyperloop is a new mode of transportation where magnetically levitated pods are propelled at speeds of up to 760 miles per hour within a tube. And the concept was first proposed by Elon Musk in a white paper called Hyperloop Alpha back in 2013. And he was proposing a route between Los Angeles and San Francisco, moving people on demand and direct from origin to destination. So it might sound a bit far-fetched and a reimagination of transport by Mr. Musk, perhaps. But then again, we've been here before, and that doesn't necessarily mean it won't happen. So to bring this concept back to reality, our guest is Ros Walker, who is the Principal Safety and Risk Consultant at TRL, a global centre for innovation in transport and mobility. In 2017, Ros published Hyperloop, Cutting Through the Hype, which offered an independent analysis of Hyperloop and its potential as a new mode of transport. So Ros will kick off 3 presentations today by providing a general introduction to the Hyperloop concept, outlining the progress made to date and the key safety and interoperability issues. And then we'll hear from 2 companies developing practical products. We have Mars Gerzer, who is co-founder and chief commercial officer at Heart Hyperloop, the Hyperloop technology provider from the Netherlands. Mars has transport innovation running through his veins. He's built Guinness World Record-breaking electric race cars in Formula One teams and co-founded the Delft Hyperloop team, which was the overall winner of the first Elon Musk Hyperloop competition in 2015. And then from Celeros, the Spanish Hyperloop developer, we have Luth Smith, their standardization and regulation manager. Luth is currently working on the business vision and strategy of Celeros. She also participates in the Spanish and European standardization committees and was previously responsible for the transport sector in the Spanish standardization organization UNE, focusing mainly on road, rail and air transport systems. So let's now pick up with Ros for the introduction, and we'll hear from Mars and Luth before coming back for your questions a bit later on. So it's over to you, Ros.
Can you see that now? Presentation?
Perfect. Thank you very much, Ros. The floor is yours.
All right, perfect. Thank you, Nigel, for the introduction. So yeah, I'm Ros Walker and I work for TRL. And as Nigel mentioned, I'm going to do kind of broad brush overview of what the Hyperloop concept is. There are a couple of bits that's repeated from Nigel's introduction, so apologies for that, but we'll just move over them quickly. So firstly, I was going to dig into straight away, what is Hyperloop? So there's lots of different concepts being developed, which we'll kind of touch upon later. But this on the slide is the agreed European definition of Hyperloop, which encapsulates all the different developers' kind of concepts. So essentially, Hyperloop is a mode of land transportation capable of high speeds and driverless operations in which vehicles are guided through low pressure tubes or systems for passengers and or cargo. So Hyperloop consists of 3 key elements. There's the system itself, which is the tubes and the vehicles that travel within them. The system has a state-of-the-art propulsion and braking systems, and also the vehicles are controlled by automatic traffic management systems. And the tubes are designed and constructed to withstand, you know, sudden air pressure changes and also take account of the low air pressure environment. Next is the infrastructure. So you'll see behind me there's a Hyperloop, which is on top of pylons. So that's one option, to have it on top of pylons. It can run along the ground, and it can also run underground in tunnels. And I think although many of the designs initially were around pylons running above ground on pylons, it's probably more likely that most of it would be in tunnels, so that, you know, I don't have so much disruption to developments on the ground. And lastly, there's the terminals. So Hyperloop developers have shared their vision of what those terminals might look like, and they're fairly similar to airports in look and feel, with check-in and security gates. The design of the hub is optimized to reduce embarking and disembarking times into the vehicles. And there'll be a series of tubes that feed into and out of the main tube that to achieve the interval rates, because obviously there's quite quick intervals between different vehicles. So that's kind of a broad brush overview of what Hyperloop is. So the next couple of slides outline why there's a need for a new transport solution and the value propositions of Hyperloop. So there's a number of key challenges that we face today which require urgent solutions. So in terms of air quality, many of the areas within Europe fail to meet European air quality limits. And transport is obviously one of the key sources of air pollution. In terms of climate change, transport accounts for a quarter of the EU's greenhouse gas emissions. And the European Green Deal is targeting a 90% reduction in transport emissions by 2050. And then in terms of congestion, many of the road networks today are heavily congested, and the cost of road congestion in Europe is estimated to be 1% of GDP. And furthermore, airports and rail networks are also operating at near capacity. So innovation in transport has arguably lagged behind other industries, leaving us with transport solutions that fall short of meeting today's challenges and tomorrow's, in fact. Furthermore, our current transport solutions can be slow, expensive, and inflexible. So in terms of the key value propositions of Hyperloop, they're on the slide. So firstly, Hyperloop is proposed to be faster. It has the potential to reach speeds of 1,200 kilometers per hour or more. So that could revolutionize intercity transport. To put it into context, Hyperloop will get you from London to Birmingham in just 14 minutes. It's proposed to be cheaper, so the capital costs are cheaper, due to the lighter infrastructure, smaller tubes and vehicles, and the operational costs are reduced due to it being fully automated and more energy efficient than other transport modes. Hyperloop is proposed to be safer by design, so Hyperloop is fully automated, so not subject to human errors. The vehicles are obviously enclosed within tube structures, so they're more resilient to external environmental factors such as adverse weather and natural disasters. And also the Hyperloop wouldn't interact with other transport modes, so it reduces the risks of collision. In terms of being more sustainable, Hyperloop is proposed to be more energy efficient than other transport modes due to the low pressure environment, which reduces energy consumption. Hyperloop is a solution that has no direct emissions, and also it's a low noise transport solution. And lastly, Hyperloop would be more convenient. So it offers an on-demand, point-to-point transport service. So the proposal is that there'll be no timetabling for Hyperloop, and that there'll be no stopping at stations along the route. So with a wide range of proposed benefits, it's anticipated that Hyperloop could disrupt the transport market, similar to other transport innovations such as Uber. And furthermore, political interest in Hyperloop is growing all the time as benefits are more widely understood. We're now seeing Hyperloop being referenced more and more in European transport strategy, but also there's significant interest in America, Canada, the Middle East, and China. It is worth noting that there is a limited appetite for Hyperloop within the UK, And this is to do with perceived challenges on our topography, so our hilly environment, and also the fact we've got lots of dense urban spaces. And there's also a political focus in the UK on the HS2 initiative, which makes it quite unlikely for them to jump ship to another transport mode. So this slide outlines the target market for Hyperloop. It's very much seen to be a solution for both passengers and freight. For passenger services, Hyperloop is aimed at providing a cost-effective, high-speed intercity transport solution for distances between 200 and 2,000 kilometres. The speeds that are offered by Hyperloop can help to offer significant economic advantages by enabling labour and commercial markets to better integrate and fully utilise nationwide skills. I guess one watch out is that obviously we've had the pandemic and COVID, and that in itself has in the last couple of years helped to bring labour and commercial markets together. So potentially, the need for a Hyperloop is diminished. Due to kind of the challenges to commercialise a passenger Hyperloop system, due to things like the safety challenges, etc., there's an increased interest in Hyperloop as a freight solution. And as per the slide, the kinds of freight that would benefit from this Hyperloop would be high-speed goods such as fresh food, medical supplies, and electronics. So as mentioned by Nigel, the Hyperloop concept, well, it didn't originate by Elon Musk. It's not a new concept. It's something, there's been many similar innovations over the last few hundred years. But obviously in 2013, Elon published the Hyperloop Alpha white paper, which open sourced his vision of Hyperloop. And obviously mentioned by Nigel was the fact that it's an alternative to the California high-speed rail development. He proposed it to be a faster and cheaper alternative. Musk himself is not working to commercialise Hyperloop. However, some of his companies are supporting the development. So example being SpaceX, which has built a test track and hosts a series of has hosted a series of pod competitions where hundreds of student groups have formed to participate within them. Some of these student groups have then established their own Hyperloop companies on the back of that, and I think mentioned was Heart and also Celeros, are both originally developed from student entities doing SpaceX competitions. So the launch of Musk's white paper sparked fast-paced innovation across the world, and it led to the emergence of a number of Hyperloop companies. On the slide are the ones that are kind of key within Europe. The first two forerunners was the US companies Hyperloop TT and Hyperloop One. Hyperloop One was formed in 2014, Hyperloop TT in 2013. And actually, more recently, Hyperloop One's become Virgin Hyperloop One because Richard Branson's invested within it. In more recent years, we've seen the emergence of significant amount of Hyperloop companies within the European context, and actually most of the R&D work happening on Hyperloop is actually within Europe now. As well as obviously Hyperloop companies, there's development of a wider ecosystem to support the development of Hyperloop, and that includes lots of different people, but to name a few, industry organisations such as engineering, manufacturing, infrastructure, and consultancy. So this slide was provided by Celeros, and it gives you a flavour of the progress to date in the development of Hyperloop, and also the projected journey to 2030. So far you can see on the left-hand side, the Hyperloop developers have fulfilled the design and simulation phase through the achievement of feasibility studies and validations of concepts and subsystems. Now they're currently establishing small-scale short test tracks as part of the validation and demonstration phase. They're also at this stage planning for the development of full-scale certification tracks covering larger distances, and this will enable them to achieve full-scale validation. These larger test tracks are necessary to allow Hyperloop to reach the top level speeds and also test the concept in its entirety. This test tracks will then enable them to develop commercial Hyperloop systems for both cargo and freight, which is obviously outlined on the bottom of the slide. It is worth noting that all of these timescales and specifics around kilometres, etc., vary between one developer and another, and the earliest projections I've seen from Hyperloop developers is for a commercial freight system by 2025 and a passenger system by 2029, or thereabouts. So as well as the progress that, that Hyperloop developers have made in terms of developing a technical concept, there's also a number of initiatives that are being undertaken within Europe to support the development of Hyperloop. So first we have the European DG Move working group, which was established in 2018 and is helping to advance the regulatory development of Hyperloop in the EU. And actually I worked on a study last year for the European Commission to help advise on what that regulatory framework needs to look like. Then we have Sensenalic Technical Committee JTC 20, which was established in 2020 and is working to basically look at the Hyperloop system standardization. Then you have Shift to Rail Hypernext, which is aimed at igniting the European Hyperloop ecosystem. And lastly is the Hyperloop Development Programme, which is a public-private partnership looking at the feasibility of Hyperloop and doing necessary tests to demonstrate its safety and identify the way forward so that we can implement the technology. There are a number of other examples as well, so you see there's quite a lot going on from a European context. The next couple of slides drills down into a bit more detail about the Hyperloop concept, both in terms of system and operational design. And really the aim of these next couple of slides is to show that there's a large variation in concepts. And indeed, the two developers that we have here tonight have very, very different concepts indeed. So some of the key features of the system are on the slide and how they vary. So in terms of tubes, there's a variation in the proposed tube diameters and also the proposed tube materials. In terms of levitation, there's two key approaches being taken. One is active levitation and one is passive levitation. In terms of propulsion, there's a variation between axle compressor-based propulsion and linear-based propulsion. And whilst the majority of developers are doing linear-based propulsion, this then also differs between linear motors being deployed on the infrastructure and the vehicle. And lastly, pressure levels. The system is designed to operate at a range of pressure levels, or different systems are doing different pressure levels between aviation pressure levels and aerospace, or moving towards aerospace pressure levels. So you can see there's quite a lot of variation in terms of system design. It's a similar picture for operational design. So in terms of vehicle size, there's some designs proposing up to 200 passengers per vehicle. And then there's others that are proposing as little as 25 passengers per vehicle. In terms of vehicle frequency, some of the designs are proposing pods as regular as every 10 seconds, moving up to pods or vehicles departing every 5 minutes. And then in terms of the speeds of vehicles, that varies a little less. But you can see Hyperloop TT is proposing a top speed of 1,223 kilometers per hour, which is significantly higher than the others. It is worth saying that for all of these are maximum speeds, and we wouldn't expect those speeds to be reached for all journey types. It just depends on the requirements of specific routes. I just wanted to put this up just to kind of give a bit more of a visual view of the differences in concepts. So the top is taken from Celeros site and shows a range of different vehicles that they are proposing for different routes. And you can see obviously that ranges from 50 to 200. But even the smaller vehicle sizes, the 50, is double the size of many of the other Hyperloop developers in terms of they're obviously proposing around 25 per vehicle. And then the bottom two pictures are from freight concepts. So the bottom left is Heart Hyperloop's cargo loop solution, which is a very small scale freight solution and would host 3 Euro-sized pallets. And then on the right-hand side, we've got Hyperloop TT's freight solution, which is a much bigger freight solution, which transports standard shipping containers. So hopefully that gives you a picture to show what a variety of different concepts are out there. So this slide is all around the kind of maturity of the concept and the technology readiness level of the system, and it's broken down into different component levels. You can see there's a high variation in the technology readiness levels between level 2 and level 7. And so whilst some of the component parts are achieving level 6 or 7, the overall Hyperloop system, the view is it's around TRL level 3 or 4. So they've kind of achieved the analytical laboratory studies to validate the concept, but not yet moved into the next level. So in order for them to achieve higher TRL levels, they need to establish more advanced testing facilities, which is obviously what I mentioned in the slides, is something that the Hyperloop developers are planning for. And for the concept to be developed into a new transportation system, it will need to achieve TRL 8. Because we're only at TRL level 3 or 4, its potential projection commercialization dates may be slightly ambitious and could take a few more years than anticipated. So the next couple of slides is to outline some of the safety and interoperability issues of the Hyperloop concept. So as mentioned earlier, safety is one of the key value propositions of Hyperloop. Just to reiterate, that's because the conventional risks of a transport system are eliminated through the Hyperloop system design. It's an automated system, so it avoids human error. The tube has no interactions with other transport systems, and it is not exposed much to the external environmental factors. However, the very nature of Hyperloop concept presents a number of key safety risks, which are obviously outlined on the slide. We're basically talking about vehicles that are operating in enclosed tubes at very high speeds, often with small intervals in very low pressure environments. So inherently, it feels quite risky. The nature of some of these safety risks will vary compared to conventional transport modes. And also the level of risks will vary between one concept and another, because obviously they vary quite significantly. So this is probably the most complex challenge, particularly from a regulatory perspective, is around interoperability of solutions. The ideal point is that the Hyperloop concepts are interoperable across Europe, so that different Hyperloop systems can operate within a unified infrastructure design. As previously outlined, there's a wide range of concepts being developed, and this has obviously implications in terms of interoperability, and obviously the key interoperability issues are outlined within the slide. There's a strong desire from the European Commission to achieve interoperability at an early stage, and that will form a key element of their basic regulatory framework. Hyperloop developers are also keen to achieve interoperability because it helps secure public and private investment, and also ensures that's a level playing field for all Hyperloop developers in the market. And as such, they will be working to converge within the research and development phase to seek the most efficient solutions based on testing. So that brings me to the end of my presentation. The slide just provides a quick summary of the key points that I've raised. There's a lot of potential and significant interest in the Hyperloop concept, both for passengers and freight, to help address existing and future transport challenges. Over the past few years, we've seen the establishment of an extensive ecosystem working to progress the concept, and they're aiming towards commercialization within the next decade. There's been a wide range of proposed Hyperloop systems and operational concepts being developed, and this presents key challenges in terms of interoperability of solutions. And at this point, the technology is still relatively immature and requires a lot of further research and testing to achieve the necessary technology readiness levels for Hyperloop to become a reality. So that's everything from me. I hope that was a useful introduction to Hyperloop. I'll now pass over to our Hyperloop developers, who will be really fascinating to hear from, and they'll tell you a bit more about the concepts that they're developing. So I think first is Hyperloop. So over to you, Mars. Sorry, it's first is Mars, so over to you.
Thank you all for having me, and I wish you all a very warm welcome to the world of hard Hyperloop, which is a world in which we envision that in 2050 we can travel across the entire continent of Europe with the same ease as you can now travel, for example, through a city, through London with the metro. And at the same time, that's basically the entire supply chain within Europe is connected within one day, to really turn it into a single market, which is, of course, one of the biggest ambitions of the European Commission. Now, before I get into a little bit more details, let's start with a quick overview of what the hard Hyperloop system is and what its main features are. Of course, the most important feature is the low pressure environment, which reduces drag, but also it reduces the noise. You can't really produce any noise if there's no air. And all of this also causes it to use very little energy usage, so that you can travel at very high speeds with very little energy consumption. The tube also isolates from the environment. This makes sure that you don't have any issues with wind, rain, snow, no leaves on the track, which also makes the system very reliable with a very low maintenance cost. The vehicles are driverless and autonomous, and that also removes any human error, which further increases the reliability and decreases the operating costs. And because these vehicles are autonomous in this protected environment, it's also possible to make sort of virtual trains in a very well-regulated manner to increase the departure rate and further increase the capacity and decrease the waiting times at the stations. Now, the tube and the columns themselves are relatively small in comparison to high-speed rail, so they reduce the infrastructure footprints, making it easier to integrate into the environment, and also reducing the infrastructure costs, because the integration parts are by far the highest infrastructure costs in the end. And these vehicles are magnetically levitated, which again makes sure that there's no noise, very little energy usage, and no maintenance costs are very low because there's no wear and tear. And finally, as a sort of a cherry on the pie, we also have a magnetic lane switching system, which allow non-stop network operations. So let me explain a little bit more why that is so important. If you look at a European network, and you look, for example, at a link between Amsterdam and Paris, that is not just a link between Amsterdam and Paris. That's actually a link that is crucial for going from Amsterdam to Toulouse, you know, from London to Berlin, from Manchester to Frankfurt, but even from Stockholm all the way to Lisboa. This link is crucial for all of them, which means that you have to take into account those network effects whenever you look at the benefits of a certain route. What this also means that if you connect, for example, a Stockholm with Lisboa, that you have lots of different places that you're passing. And what you don't want is that you have to stop at every station in between. Because if you have to stop at 18 stations, you're going to double, triple, if not quadruple the total travel time. So this is what we took into account from day one as the main requirement for Hyperloop. You don't want to connect where you have to stop at every station. You want to be able to do this, where every station is basically sort of a on and off ramp, very much like a highway, where vehicles can merge in and merge out and go at a very high speed across this core corridor. So what is the traditional technology for maglev? Well, these vehicles have their magnetic suspension basically wrapping around a track. And that means that once you want to do a lane switch, that you actually have to bend the entire track to be able to go from one track to another. So what we did from day one was we made sure that we didn't have to do that. So developed something that ensures that you don't have something like this, because this is absolutely destructive for your network capacity, because it means that you will have times where the infrastructure is basically non-continuous, right? So vehicles have to have a safe distance for that. And vehicles have to slow down, decimating the total travel times. So what we did is we're actually using a very similar system where we levitate from magnetic from steel rails, but instead we levitate from the top. And what this allows is that you don't have any track that is blocking you from doing a lane switch. You can simply pull yourself to the right or pull yourself to the left, and that allows you to make a lane switch. So let me go a little bit more into detail about how these systems work. Here you see the vehicle inside the tube with magnets on the vehicle. And these magnets actually pull the vehicle towards a steel track. So it's important to note that there's not actually any magnets in the track. It's just magnets in the vehicle. Going a little too fast. It's just magnets in the vehicle. And these interact with a cable in the track that basically propels the vehicle. So this is very much like like the electrical motor, for example, in your car, but then instead of it going round, it is the vehicle basically following the track like a linear synchronous motor. Now, when the vehicle arrives at a junction, basically all it does, it tells its guidance magnets to follow the track that it wants to follow. And as you can see, there's absolutely zero moving components in the track, making this a very, very reliable system, which allows you to go at very high speeds and even do these kinds of lane switches. Now, of course, in this tube, there is a low pressure environment. And the pressure that we're using is about 100 pascals or 0.1% of the atmosphere. Now, this is a pressure that is basically the start of what vacuum pumps do. Typically, vacuum pumps, they go down to about 0.1 to 0.01%. And that's where real vacuum begins. I don't know why it's going automatically, sorry. So we're actually at a pressure that really allows us to, that's very easy to attain, very easy to maintain, but you have to go to about 100 pascals because you still need a very low pressure to allow the energy usage to be really competitive with high-speed rail. Now, of course, what you're seeing here is still sort of a mock-up vehicle, but all of this is, of course, a model of an actual vehicle in the end, going at very high speeds through this infrastructure. To show you a little bit more about these magnets, I think this is a very cool video. Here you see us simulating a track going up and down, basically a vehicle going very fast. And then you see our magnetic suspension here with a spring damper. And then the orange block here is simulating the vehicle weight. And as you can see, when we're vibrating this track at a very high frequency, simulating the vehicle going at a very high speed, you see that the orange block is actually standing completely still. So even though you're at very high speeds, for a passenger, this is a very smooth ride. Of course, we're doing everything to really design this within the specifications also of existing rail, metro, and magnetic levitation. So that's why the accelerations that we have are all within the limits that were also set for maglev and rail. And the other specifications are that we go up to about 700 kilometers per hour. Of course, it's said that Hyperloop can go up to 1200, but for most routes, it doesn't really make that much sense to go that much faster because you need so much more time to accelerate and decelerate. And it becomes very difficult to actually align the routes alongside existing corridors. Our vehicles are up to 60 passengers, which is really the absolute maximum. We're not building Airbus A380s. This is much more about a very modern, higher frequency type of services. So we can also build smaller vehicles, but 60 is our biggest one. And the average headway is about 10 seconds, which is a safe headway for vehicles to, when a vehicle somewhere stops along the route, the vehicle behind it can still come to a safe standstill before hitting the next one. Here you see a little bit more about how that would look from a passenger perspective. We're going for a spacious design, but not something that is unfamiliar. Of course, very important, we also have things like lavatories. This is not some kind of some kind of a roller coaster ride. This is very much similar to what you would expect from a proper public transport solution. Another very crucial aspect is integration into the existing modalities and into the existing landscape. Here you see a study we did with Schiphol, where the airport in the Netherlands, where we really integrated it into their station. And here you see a Hyperloop basically in its natural habitat, where you see that the infrastructure footprint of a Hyperloop is actually very small in comparison to what we know from traditional infrastructures. And I think that's a key point to take into account here. Hyperloop is not just about going at very high speeds. Hyperloop is actually the most cost-effective and easiest to implement way to accommodate the growing demand in transport in the coming decades. If you look at, for example, a railroad, and a Hyperloop in comparison to each other, the Hyperloop is by far the smallest infrastructure footprint. The energy usage is about 10 times lower per passenger kilometer than that of road transport, and it's lower than high-speed rail at 700 kilometers per hour than high-speed rail at 300 kilometers per hour. But also the capacity is higher than Hyperloop. So really and this is already what we see so much in the markets, a lot of parties who have been looking at building a high-speed rail somewhere have now already decided, okay, actually we need a Hyperloop. And it seems like Hyperloop will come to market fast enough to fulfill the project timelines for a lot of high-speed rail developments. Here's some other aspects to show how it blows high-speed rail out of the water. Tunnels are much, much smaller, which also makes it much easier to cross difficult terrain, get closer to city centers. You can also see this, for example, with the climb that Hyperloop can have, about 6% climb versus 1.25% climb. And one of the really crucial ones is that at the same speeds, Hyperloop has about 3 times smaller curve ranges, while keeping the accelerations lower than the guidelines for high-speed rail. And this is because in the Hyperloop, it's especially hanging on top. It's relatively easy to bank quite a lot into the corners, making a little bit of a pendulum motion. All of these things make it possible for a Hyperloop to not just transport things at very long distances. The minimum distance is definitely not 200 kilometers. For example, one of the studies that we've done, or what we see here out of our network could look, for example, you could have definitely cities about 250 kilometers away from each other, but you'll definitely also have some smaller regional network with some feeder links that allow you to make a much bigger network, almost like a physical internet, where you can go from any origin to any destination. And one of the studies we've done in the Netherlands was where we, for example, looked at transporting fresh vegetables and fruits and flowers going directly from auction to auction. So it's very much also possible to make quite a dense network and not just very long distances. Now, to look at the roadmap, like also already said, we're also on a roadmap to build the first routes before 2030. Actually, sorry, this is 2026 is when we want to start building the pilot routes.
Thank you.
Let's proceed like this. This is we're going to my last slide. I think the one thing that I still wanted to mention is that we're now preparing to build this European Hyperloop Center in Groningen. The key here is that we want to test as many things as possible while keeping the infrastructure costs as low as possible. So this is actually a 3-kilometer track where we can already test at speeds up to 700 kilometers per hour. And the way we do that is by having a booster section where you can basically speed up a vehicle up to 700 kilometers per hour. Then have a test section where you can test everything at high speeds. And then a braking section where you slow down at a very high rate again. So you cannot really test anything with passengers here, but these kind of things can keep the capex low, right? Because if you want to build a full Hyperloop route where you can do 700 kilometers per hour with normal accelerations, you'd need somewhere around €1 billion. But here you can test everything for about 50 million euros. So this is really to show that everything works, and we are on planning to have this all built by 2023. So that was the last part that I wanted to highlight. So thank you for listening, and I think now the floor is up to Luz from Celeros.
So if we can do all those things, we can have Hyperloop ready by 2030, I'm sure. So I'm going to present the system from Celeros. First of all, I would like first to see how everything is growing and everything is progressing. As Ross has already said, we were born in the competition for SpaceX from Elon Musk, the same as HARD. That was in 2015. In 2017, we created Celeros. Not me, the co-founders, the 3 participants of the teams of the University of Valencia, the Polytechnic University of Valencia. They won 2 prizes, one for the Hyperloop concept and another one for the propulsion system. And by now, by 2021, we are a real company. We have growth from a startup to a really, we are an SME, but we are a real company working and progressing. And I would like to say that Hyperloop is not only the development from the Hyperloop promoters. All the Hyperloops promoters need of a ecosystem. Celeros is basically involved in the development of the vehicle, of the pod, but we need partners and providers from many other sectors, because we have to interact with the infrastructure, with the construction enterprises, with communications, with energy and electricity providers, material providers, and now we are working. We are collaborating with many partners, but I would like to highlight those 5 that appear in the slide. Acciona as construction and civil work company that is going to help us with all the infrastructures. They are also investors in Celeros. CAF, which is a really important enterprise for providing material and components to the railway sector. Now they are investing also and developing new things for the Hyperloop as a disruptive evolution of the railway, as we know. Red Eléctrica as energy company, and ArcelorMittal as provider of electric steels and developing new electrical steels, and Airbus that is collaborating in power electronics with us. So it's the work of many people together working in existing technologies, but in a evolutive way. It's important to say, because we think that Hyperloop is something like fantastic, Star Wars and so on, but we are using existing technologies. We are developing those existing technologies to provide a new way of transport. So let's go to what is most important, maybe for all of you. What is the Celeros concept and the Celeros view of Hyperloop? I would like to summarize the 4 main principles of Celeros. We are using aviation pressure levels, and additional electric aerodynamic propulsion, active magnetic levitation, and high capacity pods. These 4 are, I may say, the more differential issues related to the Celeros Hyperloop concept. And let's give a view to all of them, and I invite you to do it in what could be a trip in a Hyperloop pod. So we can start buying our ticket at home or whatever, and going to the station. The idea is to have both for passengers and also for cargo. They would be intermodal stations. I think intermodality is going to be a key word for Hyperloop. And the concept is very similar to a train station or to a railway or subway station. So we take our pod, we get inside, and we start our trip. First of all, what we need is to accommodate from the atmospheric pressure to the low pressure inside the tube of the Hyperloop system. And in the Celeros Hyperloop, we are thinking about airlocks systems in which inside the tube, the pod is stopped for a really small time, and the pressure is lower to the established one. And then once the pressure is obtained, and as I have already said, we are working at aviation pressures, we can continue and proceed with the travel, with the trip. It's important to say that one of our key points is that we are working at aviation pressures. That means about 100 millibars. We all can think what we are going to feel inside the pod, because it's the same that we are already feeling inside a plane. That means that we are using demonstrated technologies. One of the benefits of using these low pressure but not near vacuum pressures is that we are using proven technologies. The pod is going to have a structure very similar to an airplane. The materials and the components can be very similar, and they have been proved to be safe, because for air transport, there are millions of planes taking off and landing every day, and the safety is granted. We are not going to need any additional equipment inside for the passengers, just in case there's a depressurization of the cabin. We only need what is used in a normal plane travel. That means also cost effectiveness, as we are nearly, I want to say, in mass process, but it's a very industrialized process, and it's a direct path for the certification. We think that the idea is to have an operation maybe similar to the railway one, but a pod similar to an aircraft. So Hyperloop is a mix of two modes of transport that we already know. The air transport and the railway transport. And after we have achieved that low pressure environment, we have to speed up, to accelerate and go to the high speed cruise, high speed, and we use for that a launching system that consists of linear motor. We are not using the linear motors through all the line. We are only using the linear motors for accelerating in a first stage, because we are using electric propulsion, a turbofan, a compressor, as part of our propulsion system. That is because that is to take profit of two different issues. One is to reduce the cost of the infrastructure, as we are not going to have linear motors through all the line, the infrastructure is going to be more economic than if we need it. The idea is to have costs very similar to the existing cost for a high-speed railway. The cost is mainly in the pod, in the vehicle, not in the infrastructure. And on the other hand, as we are not having near vacuum pressures, we have air inside the tube. We take profit of that air and we compress, use a turbofan like similar to an airplane one, but fully electric. And we transport that compressed air to the rear part of the pod and use it as part of the propelling system. We can use also this air for thermic issues in cases of too much heating of the tube. So we can take profit of the air that is inside the tube. Then we continue our travel at the cruise speed that is around 700 kilometers per hour. Sorry, I speak in kilometers. And we continue, and the guidance systems are through levitation in an attractive levitation system. The levitation system can be attractive or active, that is using the attraction. You have one positive and one negative pole, and using the force of attraction, you can levitate the vehicle. In that case, the vehicle usually is guided in the upper part by the upper part of the tube. So you have the guided way, the guidance way in the upper part of the pod and the tube. The other way is by passive levitation. That is just the opposite. You have the same pole, and by the passive, attraction, the opposite. I cannot find the word. You are repelling the pod, and you have by ground guidance systems, and repelling, you generate that levitation. In our case, we are using the adaptive levitation by the top of the pod and the top of the tube. And then when we arrive to the station, we get inside the airlock again, this time to come back to the atmospheric pressure, and then you can leave the pod, go into the station, and go directly to the taxi, the train, the plane, the bus, or by walking, you can go home. So you are going to do a point-to-point trip via cruise speed about 700 kilometers per hour. So that's a real good opportunity for the mobility of persons, but also for the transport of goods. For cargo, it's going to be really important to have one-day delivery options. So what's next? We are working in two options. One for the passengers. We have a big capacity, very high capacity boats from 50 persons up to 200 persons, 200 passengers. We have higher highways, but we transport more persons every time. And for cargo, we are working in the transportation from 30 to 50 tons. Currently, we are developing a pilot project funded by the European Commission, by the Eurostar's funded project, in collaboration with the Port of Valencia. This pilot is going to demonstrate our linear motor, and will have also development for the transport of cargo and containers inside the ports. That will mean real reduction of pollutions and emissions in the ports, and also increasing the speed and the facility of the managing of the containers. Then we are also in Spain creating a test track of 4 kilometers length, which will allow to prove the vehicle from 600 kilometers per hour and above. So we are going to use these facilities for real speed tests. The idea is to have it fully implemented by 2025. And finally, we are participating in the expo in Dubai, in the Spanish pavilion. We have provide our first demonstrator. Is not a functional demonstrator, but is the first demonstrator from Celeros. It has traveled about 6,000 kilometers, I think. It has taken some days to get the pod there. I hope that in the near future we will have it in a few hours. So finally, and with this I end, as a standards and regulations manager, I must say that it's really important to have standards in place, but it's a must to have regulation in place so that the technology is evolving, but we need the regulatory framework not to have certification or administrative problems by the time we are deploying, or we want to deploy the Hyperloop system. And I also would like to say that having different concepts and having different technologies nowadays, it's an opportunity. It's an opportunity to have the best Hyperloop, because I think the common goal is to have a Hyperloop system in a few years. And now we are proving different technologies, and that will allow us to have the best solution, the best sustainable solution, technically, economically, for the society. So now it's an opportunity to have different concepts, the different trials and different approaches, so that we can have the best technical, the safer and the economically feasible solution in the near future. So thank you very much. I haven't said that. Thank you very much, IET, for the invitation. Last but not least, I must say thank you very much for inviting Celeros, and also glad to promote Hyperloop. Thank you very much.
Well, thank you very much, Luz. It is a pleasure to invite you here and to hear your concept on Hyperloops, and what a contrast compared with what Mars was saying just before you. And I'm certainly struck. I think back to perhaps the days of Superman. Is it a bird? Is it a plane? Is it a railway? Is it an aeroplane? Is it something different? And maybe the answer is it's all of those things.
It's Superman. It's Superman.
Certainly, when you asked if we could do a presentation, I thought Celeros and Heart were great examples because they are so different in concepts. So there are many others that kind of maybe have similarities with one or the other, but particularly these two are quite different. So it's really interesting to see the variations.
And I'm interested in the whole standards thing. This is probably your area, Ros, but Mars had a very compelling vision of the whole of Europe connected. And when we heard just now from Luz, I think I'm right in saying that there were 3 different sizes that wouldn't be compatible with each other. Presumably they're different diameter of tube. I'm sure you can correct me on that if I misunderstood. So even within the solutions that are being proposed at the moment, the concept of a completely European joined up solution is some distance away.
Yeah, I think the most important aspect here is that at least everybody has already said that the ambition is to converge to a single system, right? So, you know, the guys from Celeros are testing the technologies. We're testing our technologies. There's some other companies also testing their technologies. But we have already set up, in the meantime, this standardization group so that we can start sharing this information and really converge to one system. So, yes, you now see things that look like they're still diverging, but the whole point is, you know, you learn a lot and then you converge again. So yeah, the goal is definitely to get to that network together.
And the Hyperloop developers have been at the forefront of getting that standardization committee kind of established. So they are very keen to work towards conversions.
And I think it's marvelous that the 2 of you are on the same platform here, and at least I think we're all friends.
Exactly.
Yes. I think the goal is to promote Hyperloop. So that's if we don't work together, we can compete, but we need to work together. So I think that is a common goal for all of us, and in the standardization committee, and also in the Ship to Rail fora, all the Hyperloop companies are working together.
And I think without banging the drum too much for the IET, I think we're delighted that we can be part of not only promoting the technology, but also bringing together people with different perspectives and hopefully moving the whole world forward. That's a very grand ambition, isn't it? So not bad for a Wednesday evening in the UK. Now you've promoted lots of interesting questions amongst the people watching. So what I'm going to do is bring in my 2 colleagues, Richard and Samantha.
Hello.
Okay. So while you've been giving your presentations, Richard and Samantha have been looking at questions from the audience. So I think, Richard, you're ready to start?
Yes, I've got a question here. I think I'll aim this one at Ros. It's sort of more general question here. Obviously, there are some very high magnetic fields involved in many of these solutions. What are the implications of those high magnetic fields on people with implants like pacemakers and hearing implants and so forth?
I don't know the answer, so I'll let the other 2 answer. But I think it's not just that the impact of that. There's a lot of kind of what I think from my perspective, asking questions is what are the impacts of Hyperloop generically on people. So I think there was a question about acceleration. Oh no, there was a question about whether Hyperloop can reach speeds quickly. Obviously, it needs to accelerate at a certain level so that we're not literally being sick all over the place, if you know what I mean. So no, it wouldn't go from 0 to whatever, and very short periods it needs to build up, and that's why it doesn't work over really short distances of less than 200 kilometers an hour. And there's other things like the impact on the vibrations and stuff like that. I don't really know the answers. I kind of ask the questions around the risks, but I don't know the answers. So I will divert to Mars or Luz to talk about the electromagnetic question.
Yeah, thank you.
I can take this one. If you look at, for example, there's a maglev train in Japan, and that one uses a very different magnetic system than both Celeros and we are using, which has very large magnetic fields, and there you really need to go through a steel cage to actually walk into it. And if you look at the system that is similar to the Transrapid, also what we're using, where you have these magnetic fields really contained into the steel tracks. They are so much confined to one location, and there's lots of research already on this because it's also already, of course, implemented in the field. And this is completely pacemaker safe. The fields going towards the passenger are really low.
Good, thank you very much.
Am I right in thinking that there has been a trial with someone actually traveling in one of the Hyperloops?
Yeah, Virgin Hyperloop 1, they didn't travel at high speeds. But they did put people in the pod. Was it last Christmas, December time? A couple of the more senior people in Virgin went into a pod for a video demonstration. But yeah, it wasn't at really high speeds or anything.
And I wondered, on the sort of following up on that question, if you're traveling at high speed, if you're on a normal railway line, you get a certain amount of the sort of pitching and yawing of the cabin or the capsule. Do you think that's going to be an issue when you're traveling at high speed? Are people going to be feeling like they're being shaken up? Maybe not necessarily at very high vibration frequencies, but a sort of seasickness, if you know what I mean.
There's standards for this typically for ride comfort. You've got ISO standards, ISO 2631. It's for all these different vehicles, and it shows the frequencies and how much amplitudes you can have. So we did simulate all of this, of course, right? We simulated and looked at that we are well below the limits that you can spend 24 hours in this and still be comfortable. But I think this really is one of those questions we need to test it, because things around, motion sickness, they are so complex. And this is really one of those things that the final answer will really be that someone will have to make a proper passenger test facility, 30 to 50 kilometers to really go to those high speeds and do those endurance runs.
I mean, even the Virgin Pendolino trains in the UK make me sick. So.
Yeah, exactly. Yeah.
That's one of the reasons why we need testing facilities, because we can have simulations now at home, but we need to test the reality, because the human being is very complex. It's funny because for railway, the standard for railway comfort that is mainly focused on dynamics and vibrations is more focused on low speeds, because in low speeds the body seems to be more uncomfortable than in higher speeds, because some of the levels of the track can be omitted by the body in very high speeds. But on the other side, you have some body sickness related to the velocity and the slight curves or whatever that needs. We assume that the Hyperloop is going to be mainly a straight line, but there will be very big curvature radius or whatever, depending on the layout. And those things must be tested in real life.
And Sam, I think you've got a question next, haven't you?
Yes, I have. I think this is probably for Ross as well, but please others interject if you can answer it as well. The question was, with the advancement of Hyperloop, have we approached the government about the HS2 project and whether we can convert the rail structure into Hyperloop?
No, basically the DFT published a position paper in 2018 on Hyperloop, which is where they've said they're not really keen at the moment. They're going to kind of have a watching brief on the technology and let others go first. There has been a number of kind of pod competitions, not pod competitions, like route competitions in the UK, which is kind of doing more detailed feasibility studies of Hyperloop. And the government has, you know, paid for those studies to take place. So they are looking at it, but yeah, I don't really think there'll be a viability in terms of, you know, HS2 is what we've put our money into. So unfortunately, that's where we go. It's a massively popular project.
But you say that, Ross, but you never know. I mean, because recently the government announced that they were going to halt the HS2 from Birmingham north. And maybe that's just waiting to see, for example, how other technologies like the Hyperloop are going to advance in those years.
Yeah, I don't know. There's a few controversial infrastructure projects like smart motorways and all sorts going on in the UK. So, yeah, I don't think, I mean, I certainly haven't approached them to suggest the idea. Perhaps Mars and Luz should do it.
We have not been very active in the UK, and one of the reasons is the whole HS2 thing. And I think it would be very wise to take a look what Hyperloop does. There's a lot of governments around the world taking this exact position, right? They're saying let's, and you've got some of the biggest experts in project management and costing, like Ben Vlietberg, who are, you know, the projects not proceeding like Kuala Lumpur, Singapore with high-speed rail, saying maybe this is good because there's something around the corner that might just be a much better solution for these kind of things.
Could you see, for example, something like the Channel Tunnel being the rail being removed and retrofitted with Hyperloop? Do you think that might ever be something that could be envisaged?
I think that's much more likely than anything in the UK, but that's my opinion. Mute.
Oh, yeah, sorry. We typically are not big fans of actually removing rail because we need so much capacity, right? I would rather add capacity. Of course, there was also some question, I think, about the sizes, containers. Maybe we can cover that immediately. We think it's very unlikely you'll transport things like containers in a Hyperloop. Containers are very big. You need a tube of about 5.5 meters in diameter. We're looking more at 3.5 meters. And if you have to be able to fit containers, it means that every other route will also have these big tubes, which destroys every other business case, right? So, and if you look at why would you transport containers? They've been at sea for weeks. Why would you need to transport those in a few minutes? Typically, it's more about the higher value goods, the e-commerce, the stuff going from already a hub to another hub. So to get back to this question, I think rail, wherever you have it, keep it, because we're going to need to shift a lot of freight from road to rail. But for example, something like a channel tunnel, you don't necessarily need to also build a Hyperloop there. I think if you have a good transfer, with a European network, a UK network, and still use the channel tunnel with rail, I think the time you miss is not that large. You use existing infrastructure. So I would rather look at how do you integrate with existing infrastructure rather than having to put Hyperloops everywhere.
Makes sense.
How about from Celeros, Luz?
Yes. I think the feasibility studies must be done, and Hyperloop is not to substitute all other transport mode, is to complement. So we have to take profit of what Hyperloop will benefit. And maybe containers is not one of the issues. Just for cargo, maybe I have with I don't know, I'm just thinking plain cargo transport. I think it has different containers, for example. But everything will have to be studied and redefined, and Hyperloop will be the option when it's feasible technically and economically, both of them.
So lots more questions. Richard, do you want to fire another one?
Yes, I think I'll end this one at Luth and Miles. Maybe Luth first. Obviously, on airfields, a major problem is debris getting onto the runway and interfering with airline engines. I see the Celeros concept has got something that looks like a large fan at the front of it. These capsules are going to be moving at unbelievable speeds, at least for us sitting here today, sort of 1,000 kilometers an hour. A small amount of debris, a small amount of dust could be a major problem. How do we keep the tunnels clear of dust and debris, and how resilient are the capsules to that kind of impact?
Okay, that is one of the issues we have to study. The idea is to produce an internal environment that is always under control. The dust or the elements that can be inside the tube should not be more than the ones that are existing in the atmosphere during a flight, a normal flight, and the fans, the turbo fans, have those problems fully solved. So it should not be really a problem. One of the key points also inside the tube and for the Hyperloop system that we have not talked about today is the maintenance, the maintenance of the tube for everything, for maintaining the pressure, for checking the inside environment, the conditions, the temperature. There are lot of things that shall be controlled. Okay, so it's one of the things that we have to take into account. But in principle, the simulations and the results we have do not provide anything different to the atmosphere. Even is better because we have a control inside environment. In the outside, you can go through a fume because of anything. Now in Spain, we have in the Canary Islands the problem with the volcano that is avoiding flights. You have birds. You have many things that can cause an incident in the turbofan. Inside a controlled environment, that should not happen. So in that case, is to control and to take profit of what we maintain inside, that is the air.
Thank you. Mars, have you got any thoughts on how your system will be dealing with this?
Not really much to add. It's not a big issue for us, and yeah, we have like a 2-hour maintenance window every day where you can do any maintenance that is needed, which includes possible cleaning pods, those kind of things.
Great, thank you. I saw at the weekend when I was up on the Thames, I saw a South Western Railways track cleaning train doing its rounds, but that was spraying water all over the tracks. That was really quite messy. You wouldn't want that in your tunnels. Thank you.
Okay, so a question probably from Mars and maybe Luth as well. This is about the signalling management for the Hyperloop. So a couple of questions related to that. One is, when you have a vehicle traveling at 1,000 kilometers an hour, and you have another one starting from a station, how do they merge? How do they merge along the Hyperloop? And similarly, if you've got the tunnel going off in two possible directions, how do you signal the vehicle to go right, for example? How is that done? How is the signaling managed?
Yeah. So what you like I already said, it's very similar actually to sort of a highway concept. You've got on-off ramps, and the nice thing, actually, it fits with what you want with these on-off ramps, because there you typically have to go into more of an urban area. So the vehicles come from a station, they speed up a little bit already in that area, but you don't go very fast there, because it's nice if you can take a little bit of corners there. And then you will be speeding up towards the high-speed line. And then you basically have it come together, run in parallel for a little while it's really getting up to the same speed. And when it is the exact same speed, then it merges. And depending on the exact corridor, sometimes the vehicles on the main line slow down a little bit, just to make it a little bit easier to integrate with the on-off ramps. So it's not always 700 kilometers per hour. That's just very much local numbers. But that's the way how that works. And because these vehicles are always then traveling at the same speed, it's not like you ever have vehicles with different speeds at the same section of the tube.
Okay.
For the other question about how we actually control the vehicles, so when the vehicle departs, it actually already knows exactly what path it's going to follow, right? Here I have to go left, here I have to go right, here I have to go left. And the easy thing about the system is what it basically does is it either says, okay, I'm going to control my right air gap, or it says I'm going to control my left air gap. So it basically, by a binary switch, it just follows the track automatically. So it's a very simple control mechanism.
Mm-hmm. Is there room for that route? So you're saying it's already mapped out the route when it starts, but if there's a need to change that because another vehicle on that route turns up or whatever, is there room for that to be changed?
Absolutely.
And how is it done?
There's both a vehicle-to-vehicle communication and a vehicle-to-infrastructure communication. So, with a loss of either the vehicle with the infrastructure is able to communicate and say, you need to make a certain maneuver, right? Or if the vehicle-to-infrastructure communication is lost, the vehicles among each other are able to carry out such a maneuver. So there is redundancy in these types of communication systems.
Okay.
And how far apart in time and distance do you envisage following vehicles will be?
So right now, the state of the art of platooning for trucks, right, is about 0.25 to 0.3 seconds between the trucks. Yes, and this is on roads where you've got all sorts of things that you can't control. There was a recent study by the TU Delft that theorized that you could have headways of as little as 0.7 seconds between Hyperloop vehicles and reach capacities as ridiculous as 240,000 passengers per hour per direction, which is practically unlimited. But that is, of course, a theoretical situation. We reason first from a brick wall assumption, which means that, you've got two vehicles, one suddenly stops, this vehicle can still come to a safe stop before it.
Mm-hmm.
In theory, you could have these vehicles with headways of order of magnitude of seconds and have them really go through it as platoons. But I think the key thing is you don't need that platooning to achieve a proper capacity of 20,000 passengers per hour per direction. So it would only improve the capacity further.
It's fair to say that, I think your concept's the most close in terms of proposed 10-second intervals compared to the others. Obviously, Celeros is moving towards up to 5 minutes between. And I can't quite remember, but as far as I remember, there's not every single Hyperloop developer is proposing vehicle-to-vehicle communication. I don't know, Luz, if your system is doing that.
What is for sure is that vehicle to infrastructure communication is going to be needed. Yeah, that's sure. and probably vehicle to vehicle also.
You're still doing
probably. And I think that one thing that we have not commented is that one of the key points for the communication and for the signaling and management mechanism is really important, the speed of that communication. This is the crucial point for Hyperloop. So we will probably use the next generation technologies in communication. And I think that the development of the Hyperloop will also benefit many other different industries, as the railway, or as Mas has already said, the platooning of trucks and all those things that will take profit of the increasing capacity of the communication. The lower latency will benefit many of the digitalization on many industries. So that is one of the key factors, I think, for the communications issues at Hyperloop.
I think a broader point to make is whether Hyperloop eventually becomes a reality or not. Much of the work that they're doing will certainly help progress transport as a generic, because we're doing so much innovation in this space that, you know, that will benefit regardless of whether Hyperloop ever becomes a reality, which hopefully it will do.
So we're moving on with time. I think Richard's got one more question for you, and then we'll probably move to wrap up.
Yeah, we've got a couple of related questions related to the pressurization. So the tubes obviously have to have their low pressure maintained. So the first question is roughly how close together do these pumping vacuum stations need to be? And what happens to the passengers if, heaven forbid, one of the cars develops a leak and suddenly the pressure drops within it? To Mars and Luther, I guess, for that one.
So in principle, you need these stations actually very far apart from each other. Basically, how we do it is we've got sort of dedicated, really strong pumps that can bring the system to a very low pressure, right, 100 pascals. And then you've got a different set of pumps that are really efficient at keeping the pressure at that level. And so one is very high power, the other is very low power. And in the grand scheme of things, the power of the pumps is negligible in comparison to the energy we still use for actual aerodynamic resistance. So we actually can put them tens of kilometers away from each other, these pumping stations. And there, you can just imagine it's like a small container that you can dig into the ground. It's not a very big deal. What we do have is that we will probably use some kind of a movable large pump, so that if there's an emergency situation, and that's exactly your second question, and there's some kind of a pressure loss in the vehicle, we have a process where that vehicle and the vehicles behind it come to a safe stop, and that section of the tube can be very quickly repressurized.
Right.
You can do this within a time frame where you will never have an unsafe pressure for the passengers. But of course, this means that you do have a section that is pressurized. So we have a movable pump that you can bring there to repressurize that part also very quickly and bring it back into operations. But basically, you repressurize, and then it's very much like a tunnel. We're using the same distances between emergency exits for normal tunnels, where passengers can just exit the front and the rear of the vehicle and go to the nearest emergency exit.
Okay, thank you.
Well, I think that's got through quite a few questions. I can see there were an awful lot more that people put forward. Sorry we didn't have time to cover everybody's question tonight, but I think a very interesting conversation from our three guests today. And the whole concept of Hyperloop, I'm certainly a lot more informed than I was when we we started this evening's event. And interestingly, if I think back even to my my school days, there was a chap that popped along from the local university and demonstrated magnetic levitation, and we all thought it was somehow something that was rather futuristic and would never have any application. But well, here we are today. So on behalf of everyone watching, I'd really like to thank Ros for leading us with the introduction, and both Mars and Luz for giving us the benefit of their very different takes on the Hyperloop concept. That's pretty much bringing today's activity to a close. Just a quick word about what we're doing next for people interested in engineering and technology in not only the area around the IET Surrey, but anywhere you care to listen in from. And our next speaker actually is Neil Freeman. He's from the Nikon School of Photography. And the presentation he's going to be giving us is Life Through the Lens, Technology Behind the Art Form. This is primarily directed towards children and younger people who may be considering a career in education and going on to study engineering and taking up engineering careers. And I think that one of the things that inspired me both about Mars and Luth was the projects that came out of student competitions, and I think that's a great indication that if you've got an idea, you can challenge what the convention says and come up with something that's really interesting. So next month we're going to be looking at photography. Life through the lens, and because photographs can capture all sorts of meaningful memories and breathtaking views and so on, this is really a primer on how to take great photographs. So if you're interested in that, do come along and you'll find us in the usual place. Other than that, it's again, thank you very much to our three guests today. First time we've had three guests together, so thank you very much for that. And I wish everybody a good rest of the day, wherever you are.
Thank you. It was a pleasure.
Thank you very much. I hope you see you soon.